Very good morning, dear friends. Welcome in this video lecture. Dear friends, we are discussing from our last video related to atomic fluorescence spectroscopy. In last video we have discussed about what are the basic concepts, fundamentals of this atomic fluorescence spectroscopy, that is AFS. Then we also discussed about the ruby laser. So that is, ruby laser is one of the important line source of electromagnetic radiation that has been used in the AFS spectrophotometers. Today we are going to see the details about cells or furnaces, means the sample holders that has been used in atomic fluorescence spectrometer. So what is the need of these cells or sample holders in AFS? We know that we can use either a line source or continuous source for the excitation of the atoms or ionization of the atoms from the ground state to their excited state. For this we must need a electromagnetic radiation, an electromagnetic radiation in the form of laser or halocathode lamp or plasma that we must need it. Okay, and once the pulse or continuous source has been emitted by these electromagnetic radiation sources, then the atoms must be present, our sample or the atoms of our sample must be present within the particular path length, to absorb that radiation and further consequences which are occurring in the AFS. So what is the need of this cell? Cells are known as furnaces. Cells are also known as furnaces in the atomic fluorescence spectrometer. So what is the need of this cell? So if you look this figure, this diagram, okay, which indicates the two mirrors placed at the two ends of this optical path, okay, and in between these two mirrors the optical system is placed here. Okay, so this is the F stands for flash lamp. Okay, this flash lamp is nothing but a source of electromagnetic radiation. It may be either halocathode lamp, electrodeless discharge lamp, lasers, it may be ruby laser or excimer laser, or it may be ICP, that is inductively coupled plasma. So this flash lamp is producing electromagnetic radiation, and that must be absorbed by our atoms of the sample, and hence to hold these sample atoms, to hold the atoms of that sample for a longer time, we must have a sample holder, and that sample holder is nothing but cells or furnaces. That sample holder in AFS are called as cells or furnaces. Okay, so this is a typical diagram of this AFS is shown here, in which F is some flash lamp source, okay, and here the cell or furnace is used, and which is pumped dye solution, in which dye solution is pumped from this is inlet and this is outlet. Okay, so a dye solution is responsible for the fluorescence to occur. Okay, that is a source, or that is a media, what we can say. Okay, and in this a pumped dye solution is pumped from this inlet, and it is go out of this cell from this cavity or from this region. Okay, so the flash lamp is producing flash. Okay, that radiation is get absorbed by our atoms of the sample, in which atomization or ionization of the sample must take place. Atomization or ionization of the sample must take place in this cavity, in this region. Okay, so to absorb maximum light, to absorb maximum radiations from this fluorescent lamp, the path length of that cell must be enough high, okay, or enough lengthy. So this is the need of cell. Then there may be a chance of background emission due to the thermal excitation. Due to thermal excitation, the atoms of our sample may get thermally excited. Thermal excitation is rather different than the excitation of the atoms from the fluorescence, from the flash lamp radiation. Okay, so thermal excitation means when the atoms of our sample is exciting from by capturing the heat by gain in the temperature of the system, they may get excited. So this may give wrong results, wrong analysis. Okay, so that's why to avoid this background emission, this is known as background emission, and to avoid this background emission, the temperature of that system, whole system, must be kept as low as possible. Okay, temperature of system must kept as low as possible. Okay, so this is the minimum condition, but this should not be very less so as we require excitation at optimum temperature. So for optimum for excitation to occur, the optimum temperature is necessary, so that why a particular temperature range or optimum temperature is necessary for the excitation of the atoms, or atomization or ionization of the atoms in the sample must be takes place here. Okay, then the burners we have already discussed in atomic absorption spectroscopy that the premix burner or total consumption burner have been widely used in such type of spectrophotometers. So both of these types of burners, that is total consumption burner and premix burner, both type of burners can be used in AFS. Then the next one is flames. So what are the flames that have been used, or what are the sources of oxidant and fuel gas that have been used for the formation of flames in the atomic fluorescence spectroscopy? Okay, so it is a flame spectroscopy. We are using flame here, and here the different combinations of flames can be used. Okay, for example, air plus hydrogen. Here air is acting as a oxidizing agent or oxidant, and hydrogen gas is acting as a fuel. Or another example may be air plus acetylene. Acetylene is a gas at room temperature. Okay, it is alkyne C2H2. Or nitrous oxide, N2O, nitrous oxide plus acetylene can be used. So these are the different options available for the choice of flames. Which flame we have to use here? There are three choices. Okay, then furnaces. So these cells are nothing but furnaces. So why they are calling furnaces? Because we are using flames here. Okay, and here the atomization or the ionization of the sample takes place, and hence different furnaces can be used. Okay, out of which the two are more common. For example, the graphite. Okay, the graphite is there, and one other is there, carbon cup. Okay, so graphite is also an allotrope of carbon. Okay, so graphite tube is there. Okay, graphite tube is there, or you can use carbon cup. Now in modern instruments, there are different variations can be observed for these carbon cup furnaces, carbon cup cells for this AFS. Okay, so this is all about the cells of furnaces that is used in atomic fluorescence spectrometers. Okay, now we have discussed so far from the last 2 to 3 videos about the different electromagnetic radiation sources that can be used for the atomic fluorescence spectroscopy. Okay, here the one more option is there, one more source can be available nowadays. Okay, and it is known as plasmas. Okay, so what is plasma? Plasma is nothing but a coexistence of of atoms, we call it as a neutral atoms, then electrons and ions, that are positively charged ions, cations. So this mixture in a system is called as plasma. How it is formed? Generally, for the formation of plasma, we call it as an inductively coupled plasma, ICP. Or if we use argon gas as a source of plasma, then it is also called as ICAP. So what is ICAP? ICAP is nothing but inductively coupled argon plasma. What is this actually? So plasma is nothing but when an argon gas along with that our sample, okay, so when argon gas is used, okay, and we use that argon gas for the formation of plasma, okay, in that, with the help of seed electrons, seeding of electrons means for initiation of that fluorescence, initiation of that process, we must add some electrons by a discharge, by an electric discharge. Once these electrons are entered in the system, then these electrons strikes to the neutral argon atoms, okay, and when the neutral argon atoms are strike to these seed electrons, further ionization of the neutral argon atoms takes place into argon cations and electrons. So this process will now be in continuous. We call it as a self-sustained process. Very easy to understand. When these excited electrons, we call them as a seed electrons, strikes with the neutral argon atoms, okay, then there is a formation of ionization of this neutral argon atoms takes place to argon cations, plus the electron which is ejected from this neutral argon atom, plus the energy released electrons, the electron which strikes this argon, okay, now it is in ground state, okay, the energy of this electron is get delivered, it is released to this argon, okay. So number of electrons get multiplied in this process, and such a mixture is formed, such a gaseous mixture is formed, and that gaseous mixture is nothing but plasma, okay. But here in this state, in this physical state of that matter, all these three species, chemical species, that is argon, neutral argon atoms, electrons and the argon cations, that is ions, are existing together, and that system is known as plasma or inductively coupled argon plasma. Now why it is called as inductively coupled? Because an magnetic induction have been introduced with the help of a copper coil, okay, a cylindrical shape is there, okay, and in this cylindrical shape of apparatus there is a central tubing is there, through which argon gas and electrons have been introduced, okay, and then here there is another source, it is called as secondary or second source of argon, okay, and they meet at this region where the copper coil have been introduced, okay, and this, through this copper coil, radio frequency is applied to this top of this cylinder, okay, and due to this the argon gas, ionization of the argon gas has been taken place, okay, and here the plasma, formation of plasma takes place here in this region, okay, formation of plasma takes place in this region, and this is known as, this is the typical diagram of a ICAP, that is inductively coupled argon plasma. Okay, and this can be used as a source of electromagnetic radiations. Okay, so when this argon gas is excited, argon gas is excited, then while falling down to the ground state, they emit radiation at particular wavelength, and hence such can be used as a source of electromagnetic radiation. Okay, so this is all about plasma. Okay, now the next point is the wavelength selector. So which wavelength selectors that has been used? Wavelength selector. What is the need of wavelength selector? Okay, we know that wavelength selectors are used for the, these are the wavelength selectors. Lambda selector is nothing but wavelength selectors. These are used for the selection of a particular wavelength. Okay, and for this generally monochromators are used. For this monochromators are used. Monochromators means these are the devices which are used to select a particular or single wavelength of that radiation. Okay, such monochromators have been used for this selection of incident radiation that has been prepared in the cells or the furnaces in the atomic fluorescence spectrophotometers. Okay, then here both manual and computer generated monochromators manual or computer operated monochromators that can be used in this wavelength selectors. Okay, then if a line source is used, then monochromator may be of low resolution type. If a line source such as laser, if we are using laser as a source of radiation, which is known as line laser or line source, then in this case the monochromators can be low resolution type. So we have a chance that we can use low resolution monochromators for line sources. But if continuous sources are used, continuous sources for electromagnetic radiation such as ICP or plasma, then the monochromators must be of high resolution. Monochromators used must be of high resolution. Okay, and here line source for low resolution. Okay, so these types of monochromators can be used. Okay, then detectors. So what are detectors? So these are the devices which are receiving signals from the sample. Okay, so excitation of the sample atoms takes place, then it may fall down to the ground state, and while falling down to the ground state they release energy, they emit radiations. That emitted radiations is known as fluorescence, and that fluoresced radiation, when it is focused on the detectors, that detectors will analyze the signal, convert it into an electrical signal, and gives the that signal to the readout devices. Okay, so detectors have an important role in the AFS also. Okay, and very famous detector, that is PMT, it is also used in atomic absorption, atomic emission spectroscopy. Okay, so that's why the photomultiplier tubes is commonly used detector in the atomic fluorescence spectroscopy also. Okay, other may be used, but they are of very little use. Okay, so widely used in the world is photomultiplier tube as a detector in the atomic fluorescence spectroscopy. Okay, so this is all about the instrumentation part of this atomic fluorescence spectroscopy. Okay, I think you enjoyed this video. Thanks for watching this video and have a nice day.